Well, it does just that, except it does it automatically. So what we have, we'll be talking more about all parts of the machine, but for now in particular, we have this set of cogwheels. This is kind of the calculating portion of the machine. You can see there are 8 vertical stacks or columns. They're organized according to the example on the board. So on the left, we have the result column. We have first difference, second difference, and so on up to 7th difference. So this machine calculates these polynomials up to 7th order, or lesser order ones just simply by not utilizing the higher order cam stacks. It computes the result on the left. Now, how does that work? Well, perhaps shall we spin a little bit more? Or
sure.
We had some background noise this morning, so we did more talking, but perhaps we can do some spinning and I can talk, I think, loudly enough so we can talk about what's going on. Okay, so Ray's doing his upper body workout, and he's through this gear train. He's driving this cam stack. Now the cam stack comprises 28 cams, and they're actually in pairs, so there are 14 pairs of 2. Each pair has a kind of symmetry that takes advantage of pipelining, and that's one of the ways Babbage was able to obtain his 3x improvement that I talked about. So the cam stack now is driving this, if you will, transfer mechanism here. So the rotary motion of the cams is being translated into linear motion here in 2 dimensions. So you hopefully saw some levers going horizontally, and also you saw some vertical motion of the cogwheels, again, as Ray did his cranking there. So what this thing is doing is it's basically driving this calculating mechanism in a way that implements this mathematical equation. Now, so I mentioned that the cams are organized into 14 pairs. Why is that? Well, it turns out that in every cycle of the machine, and one cycle corresponds to 1 rotation of these large gears and 4 rotations of the crank. By the way, I'll digress just slightly. You'll notice if you look on the end that this hand crank can be attached either here, where Ray's using it, or here. So we can get 4-to-1 reduction, which Ray is using. Or when he progresses and develops his upper body enough, it will be a while. And being facetious, as it turns out, it's humanly impossible to do anymore. That's one of the differences that we sort of figured out, if you will, that were necessary to make the machine practical versus Babbage's original design, and I'll talk more about that. But getting back to the point, for every cycle or rotation of this cam, you can see some notations on this plate here corresponding to divisions of that cycle. There is one result produced, okay, and that cycle is divided basically into 2 halves. So there's a kind of pipelining such that in one half, the odd results, or the odd cam stack results, are added to the even, and then on the second half cycle, the even are added to the odd. So in parallel. So those 2 things happen such that all odds are added to all evens, and then all one half cycle evens are added to all odds in the second half cycle.
Called parallel processing,
right.
Which those of us who are geeks know all about in our computers.
Right. Okay, now what about these cogs? Several things. Each cog, so each difference or the result, represents a 31-digit decimal number. So we have practically up to about 30 digits of decimal precision. So we could go far beyond the kind of precision that were available in those early tables. Practically speaking, that's probably more than enough, but part of the beauty, the genius of the design is that we can actually work on 2 problems at once. So we can divide the, if you will, the cog space into 2 parts, and that's actually what we've done now. So it turns out the bottom 4 cogs of the cog space are devoted to just running a counter that counts the number of iterations, and when we read off the chart, that's how we were able to select the appropriate result, which is according to the index number, which is spread out on the bottom 4 wheels of the result column. So the remaining 27 higher cogs are devoted in this case to the actual problem. Now, I have a quiz question for you, and it's going to be an easy one. Do you think this machine, based on what we've said so far, is an analog or a digital machine? And a hint is that there's no wrong answer. Many opinions.
Well, it seems digital, but it doesn't seem to be any continuous states.
Okay, you get a result that's discrete. decimal number, which is a digital kind of thing. But on the other hand, the rotation of these components, the race and analog human, his rotation is continuous, and basically all the stuff in the cam stack and through here is a kind of continuous kind of motion. So it is in fact a digital machine. So what causes the analog characteristics of the mechanical motion to yield a digital result? Well, in part, it's these things, and it's maybe a bit hard to see, but if you look closely, you'll see a number of blades or swords here, and those have a kind of digitizing function. So if you look closely at the cogwheels, you see the reason they're called cogwheels is they have these teeth, or cogs, almost like ear teeth. And what's going on there is that in the appropriate part of the cycle, I'll model these cogs with my thumb and index finger. The wheels advance a certain amount. There's an ideal position, which would be, let's say, here, but because of an accumulation of errors, backlash, and tolerances and so forth, a wheel might end up in a little bit different rotation angle from its ideal position. So at an appropriate point, the knife comes in and causes the wheel to register in the appropriate place, which is what gives it its digital nature. Now, that's a kind of error correction. There's also a kind of error detection. Now imagine that particular cog, let's say after a few billion cycles and a few hundred years or whatever of use, there's so much wear that a particular cog ends up exactly in between either of two ideal orientations. In that case, the sword would come in and land exactly at the high spot of a particular cog. And any ideas what would happen if that were the case?
Because the sword can't
Would freeze up, right? So that's its model of error detection. Okay, so that fortunately doesn't happen, but that is built into the machine. So it's far better to have the machine freeze up than to give an erroneous result. So it's a kind of combination error detection and correction that is.
By the way, the rhythmic clanking sound, rather loud, is this locking mechanism slapping in and centering the finger.